Yeah, hello and welcome back. So we are discussing about state space realizations, and we also saw how we can derive state space realizations from physical systems by understanding their physical behavior and the laws governing those behavior. So we derived state space relations for a mechanical and an electrical system in class, and we also saw that when a system will be represented in a block as a block diagram. So many times we represent our systems in block diagrams with the basic block diagram elements of the integrator, gain and the summer. So if such a representation is available, then also we can make a state space realization from those block diagrams. So those are the two different avenues from which we can make the state space realization, and today we will be discussing about deriving the state space realizations from transfer functions. So transfer function is one very important avenue from which we derive state space realizations. However, this is only limited to linear time invariant systems, as you all know, because transfer functions are defined only for LTI systems. However, this is an important avenue of deriving state space realizations because it reveals a very important feature of the state space realizations, which we will discuss as it comes to us. And also we know the transfer function of various processes, and we can use that knowledge of already we know how the transfer function will look like for certain processes, not a specific system but a certain type of process, like you know that there are first order time delay processes, there are second order processes. So if we know such a process, if we know what its transfer function is, then we can just take that transfer function and derive a state space realization from that. So that's why understanding this section is very important. Also, in many industrial practice, many and in general case, you will see that the transfer functions have been defined for a particular system that you are working with. So if you want to extend the or if you want to dig deep into that system using the state space realizations, you can directly start working from the transfer function. You don't have to go into understanding the actual physical laws governing the system. So you have the transfer function, and you straight away from there you can derive the state space realization, because many a times it so happens that the physical system description is not available. However, the transfer function could was derived through some ways. There are many ways of identifying system transfer functions using input output method. So identification methods are available. So transfer functions could have been developed for those systems, and you can simply use those transfer functions, and whatever ideas we will be discussing now, you can use them to make the state space realization from those transfer functions. So with this introduction, we move ahead and just look at the first form that we derive from the transfer function, and this is called the first companion form or the phase variable form. So these are various names you will find, and it so happens that for me particularly I tend to forget the names of these forms. However, the names are not so important because you must understand how you are proceeding from the transfer function and landing to the state space realization. So that understanding is important. The names doesn't matter so much. However, if you can remember them, that is better. So and for the purpose of the course, at least as long as you are in the course, try to remember these names, because it may so happen that in the exam one can just ask derive the first component form, or derive the phase variable form. Then you cannot derive any other form that can also be derived from the same transfer function, that we will also see. So we will see several forms being derived from this same transfer function. So one may ask derive the phase variable form, then you cannot derive any other form. So that is also something one needs to understand, and we also had discussed it slightly in the last lecture, that it is possible that we can derive another state space realization from the same system. So state space realizations are not unique, even though the system is unique, even though the transfer function is unique. A transfer function is unique, however, the state space realizations that will be derived from this transfer function will not be unique. So there can be different state space realizations. So with that note in our mind, we first discuss some very popular state space realizations, and then we will go into that understanding that they are different, so but they are coming from the same system, so there must be some relationship between them. So what is the relationship, and all those things will be discussed, will be taken up in further lectures. So in this, let us understand the first companion form of the phase variable form, where we are dealing with a generic transfer function. Generic because you see that the numerator is of the same order, so it can happen that the numerator is of the same order as the denominator, but it cannot be more than that, because that will make the transfer function improper, and we are not dealing with improper transfer functions. I request you to brush up your ideas on these terminologies that we'll be using. If you don't find some terms familiar, then just go back to your control system first course, and see where those terms has been used, and gain that understanding. And you can also ask me in the doubt clearing sessions. So this is so since the transfer function has to be proper, it may not be strictly proper, but at least it has to be proper. So the numerator order is same as the denominator order in a generic transfer function. Now please note that this b0 b1, these bi's and these ai's, they need not be non-zero always. So some of these could be 0. So mostly you will find that this b0 is 0. So when b0 is 0, then this transfer function becomes a strictly proper transfer function. Otherwise, if b0 is non-zero, then it remains a proper function, proper transfer function only. Similarly, any of these coefficients could be 0. However, at least we know that at least in the numerator we must have one coefficient, this bn, and it can be 1 as well as it can be any constant. So with that idea, we actually first break this transfer function down into two transfer functions. As you can see here, the first one is the more simple one. So zs, some intermediate variable z we have defined, and we define zs by us as only the denominator with numerator as only 1. Okay. And then we define ys by zs as only the numerator with no denominator there. So denominator here is 1 basically. And if you see, if you multiply these two transfer functions, you will get ys by us, which is this transfer function. So we have simply broken this down into two transfer functions, and we will be dealing with these two separately in order to go ahead in formulation of the SPR. From this transfer function Zs by Us, what do we get? We very easily get this relationship. D is the differentiation operator. So the differentiation Sn means, so Zs in time domain is becomes dnz, that we all know. So from the Laplace transform and inverse Laplace transform identities, we know this, that Snzs going to the time domain will become dnz. Similarly, all of these we very easily know, and Us becomes u. So what happens here? So and so we take this side and do some algebraic manipulation, taking the other all the terms to this side apart from this dnz, gives us this equation. Now what we do, we define the state variables. State variables are always defined with x, x1, x2, x3, x4. So xi's are always used to define the state variables. There are also like any variable could be used, but this is the mostly used convention, or at the very beginning we try to use x, and if we find that we also need some other representation, then we move to some other variables. So normally we begin with x. So what we did here, we defined z as x1 and all the other state variables as in this fashion, all the other state variables as the derivative of the preceding state variable. So you see xi plus 1 is defined as xi dot. So x1 dot would be x2, x2 dot will be x3, and this we continue doing for all the n minus 1 state variables. So one question, how many state variables will be there? That we already discussed. It will be as many as the order of the system, which we can easily see from the denominator transfer function, the maximum order of S. So there will be n number of state variables. So from x1 to xn minus 1, we use this relationship between these state variables. Between the state variables x1 to xn minus 1, we use this relationship. We define x1 as z, and then we continue defining x2 as x1 dot, x3 as x2 dot, and xn if I put I as n minus 1, then it becomes xn. So xn as xn minus 1 dot, xn as xn minus 1 dot. Okay. So what is xn dot now? Xn dot we have not defined in this way, but if you look closely, xn dot, so since xn dot is xn minus 1 dot and xn minus 1 is xn minus 2 dot, so in this way if you proceed backwards, you will find that xn dot is basically x1 nth derivative of x1, like dn x1. You will find that xn dot becomes dn x1. You have to proceed backwards using this relationship. So xn dot, you will find it is dn x1, which is basically dnz, which is basically this. And then you look at the right hand side, and in the same manner that dn x1 is dnz, you will find that xn, here you see that an, this z is x1, so we have written this a minus an x1, then this dz is what? x1 dot, which is x2, so we have written this minus an minus 1 x2, and we go this way, and we come to this, which is a1 dn minus 1 z, which is xn minus 1 dot. So xn minus 1 dot is xn, so we have written here xn. So this relationship and this going backwards through the differentiations and coming to this same equation again, that thing you need to look into. So I suggest that you write all this, or at least expand this a bit, x1 dot, x2 dot, x3 dot, then again from xn minus 2 dot you start. Xn minus 2 dot is xn minus 1, xn minus 1 dot equals to xn, and xn dot equals to what? So then you will see that xn dot is basically dn x1, and then you can write this term in the right hand side, and here instead of this z dz to dn minus 1 z, you can simply write this x1 to xn, and the u remains as it is. So when you come to this equation, you arrive at this equation, then you see that all the dynamics, all the first order differential equations of the state variables are with us, and that gives us the state space realization of this transfer function zs by us. Zs by us is this particular transfer function which has numerator as 1 only. So this is the SPR from this Zs by Us transfer function. If we write it in this manner, Ax plus Bu Cx plus dz, then we can say what is A, what is B, what is C, what is D. Looking at this set of equations, we can very easily identify that A will be like this 0 1 0 0 0 0, because x1 dot is x2. So if you have you multiply this with the x vector, you will get x2. Then x2 dot is, you multiply this row with the x vector, you will get x3. So it will be 0 0 1 0 0 0 0. So in that manner we continue, and the last but one is xn minus 1 dot, and we have to make it xn. So we have to multiply this row, last but one row, with the x vector and get xn. So only the last element will be 1, all the other elements must be 0. So you must be very confident in operation with matrices and vectors. So that's why some preliminary material was also delivered to you. You should go back, if you are not very confident, you should go back and brush up your practice in working with matrices and vectors. So this has to be in your fingertips. So here xn minus dot will be like that, and xn dot is minus an x1 minus an minus 1 x2 and going ahead minus a1 xn, the last term, and there is u associated with only the xn dot dynamics, not any other dynamics. So b, which multiplies with u, so bu, so b will have all the elements as 0 except the last one, which is 1. Last one will be 1. What is C? Z equals to cx plus du, z being the output here, z equals to cx plus du, and z is basically x1. So what would C be? C will be 1 0 0 0 0 and d will be 0. So in case you have a transfer function like this, where there are no zeros in the transfer function, there are absolutely no zero, so this is the SPR that you obtain in the phase variable form or the first companion form. Okay, then simply you change this z to y, that's all. However, we have the generic transfer function, so we have to deal with the zeros. So how we deal with the zeros? We will take the idea from, we will extend this state space representation and will include the zeros. So before we do that, we just look at the block diagram of the same state space representation. So you have to look at it a bit careful, because it's the first time you are looking at a block diagram representation coming from such generic transfer function. So just pay attention here. What we have done, you see that this is the output y I have written here, and this is the z actually. So since we have no zeros, so y is actually z, So I have written here y. Now you see how we had defined the state variables. X1 dot, which is x1 dot is in this side of the integrator, is equals to x2, which is the output of this integrator. X2 dot is in this side of the integrator, which is x3, the output of the next integrator. So in this way we have formed a chain of integrators. So this is also sometimes this sort of SPR, the state space realization, is also known as the chain of integrator system. Many a times you will find this expression chain of integrators system. So chain of integrators means A matrix will take this form. A matrix will take this form. What is the form? The first row will be 0 1 0 0 0 0, second will be 0 0 1 0 0 0 0, like this. N minus 1th row will be 0 0 0 0, final element will be 1, and nth row, the last row, will only have coefficients, not any other rows. Only the last row will have all the coefficients. The other rows will have only one non-zero coefficient, which is 1, and they will be like this, a bit this like the diagonal was 1, but the diagonal got a bit shifted to the right. So it is like the upper diagonal. This is called the upper diagonal. So the upper diagonal elements are 1 in this case, and the last row are all non-zero, and the rest of the elements are 0. So this is the form of the chain of integrators, because the block diagram looks like this. When you draw the block diagram from this, it looks like a chain of integrators. Now this integrator chain will end somewhere. It ends with xn dot. Now xn dot is not any we can't have any other integrator here. So xn dot is what? Xn dot is all this expression that comes here. So xn dot must have this u. First thing, u is coming here, and all these other signals, x1, x2, x3, x4, all these other signals up to xn, getting scaled by these coefficients. So like you see, xn getting scaled by a1, x1 getting scaled by an. So all these are getting added, added, and then coming through this. Okay, one mistake is here. This should be minus, because you have minus sign everywhere, na? So this I have overlooked. So please, when you are making your notes, correct this. So this plus should be minus, because you have to, these all are coming with the negative sign, and this u is plus. That is fine, u is plus. So I hope you understand how this block diagram is coming from this SPR. But this is only when you don't have any 0 in the transfer function. Now we include the 0 and see what change happens. So we include this 0. So we have to deal with ys by zs. Now already we know what z is. From this particular transfer function we have figured out what z is. Now with that same z, we are trying to see what y is, because y will be what? Y will be simply b0 dnz plus b1 dn minus 1z plus dot 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 plus bnz. That will be y. So whatever output we had already obtained, y is basically a series of differentiations taken on that same output. So it is a summation series of the differentiations taken on that same output, scaled by some coefficients. That is all. Now how we construct the SPR, how the SPR changes now. So we don't change the definition of the states, we keep the definition of the states as they were. So we have the same state equations. The state equations are not changing. Z was x1. So now you see, since z was x1, the y equation can be represented in terms of the state variables that had been defined, because z is x1, dz is x2, dn minus 1 z is xn minus 1, and dn minus 1 z is xn, and dnz is xn dot, dnz is xn dot. This we have already understood. So we write the y in terms of these state variables. Z is x1, dnz is x2, and dn minus 1 z is xn, dnz is xn dot. And since we know what xn dot is, we don't want to keep any dot here. We want to express the y in terms of the state variables only, not their derivatives. So we we know that this derivative from the state equations we already know. So we replace xn dot with this expression, we replace it, and when we replace it, doing some further combinations, collecting the states, the coefficients of the states, we get this expression. So this is a step jump here. You do the intermediate step yourself, you write the expression of xn dot here, and then you expand it, and then you collect the coefficients of each of the states, x1, x2, x3 up to xn, and then we also see that this b0u also comes. So now you get the expression of y in terms of these state variables. So only the y equation changes, the x equation does not change, the x dynamics does not change, only the y equation changes. And then we can express it in terms of ABCD once more. Only you will see that C and D has changed, A and B remained as they are. So that's why the form remains same. So even if you have a no zero and have so many zeros, the state dynamics does not get affected. In this particular form, the state dynamics does not get affected. Okay, so the state variables are sometimes also called the phase variables in this case, in this representation. So this is C here, and you see that previously the C was 1 0 0 0 0. Now all these coefficients have come here and occupied the places, and D has become B0. Now there is a comment that for proper this should be strictly proper, for strictly proper transfer function B0 will be 0. For strictly proper transfer function B0 will be 0, and hence this C will reduce to only the coefficients of the numerator. So this B0 will vanish, right? This term will vanish. So the C will be Bn, Bn minus 1 up to B1. So all the n coefficients from Bn to B1, that will be C. Okay, so it reduces to the coefficients of numerators only, and D vanishes. So this is the comment. And now we look at the block diagram. So this block diagram comes very straightforward from the SPR. So this part remains the same, the chain of integrators, and the lower part of the block diagram remains the same because it is what was forming the state dynamics. Now we have to form the output. The output has to be formed differently. Before, the output was simply taken out from x1. Now the output has to be taken out as a summation of all the states passed through some gains. So you see x1 being passed through Bn, x2 being passed through Bn minus 1, like that. So xn is passed through Bn, x1 is passed through Bn, x2 is passed through Bn minus 1. So this is happening, and furthermore what is happening here, and note that this must be negative, this must be minus. So this is something I have mistakenly put here plus. Now this xn dot, this is passing through B0. So you see we have actually taken this equation, and this would be same as this. Of course this would be same as this. So we pass the xn through B0 and then add it up. So we pass the xn dot through b0 and then we add these things up. So it will give the same equation, the same SPR getting represented by this block diagram. So instead of scaling all these things by this minus b0n minus b0n minus 1, so putting all this here, we have simplified it a bit by taking xn dot, passing through b0 and adding it to all this. So that is equivalent to including these terms minus b0 ai in all of these blocks. Now if we have and also one thing we could achieve from this is that u is also getting passed through b0. So d is equals to b0, so u must also get passed through b0 and get added to give y. So this is also happening in this block diagram representation. If we find that it is a strictly proper transfer function, b0 will be 0, so this block would simply be taken out from this block diagram. So that is about first companion form, and there are some remarks you can go through this. This is some observation I had made. So one can consider this integrator chain. So it is sometimes easier for you to remember when you are first dealing with these representations, because it is a conversion from transfer function to state space realization and to block diagram. So all these are in the same discussion, so it might become a bit overwhelming, but to avoid that you can try to find out a pattern between all these things. So that pattern I have pointed out. You may consider that this division, the division line of the transfer function as this chain of integrators. So if you do that, you immediately observe that the gains are in the same order. So the gains in the in the top of the integrator chain is the gain of the numerator. The gains in the bottom of the integrator chain are the gains of the denominator, and in the same order they are appearing. They are appearing in the same order. However, the states are in the opposite order. So the output of the first integrator, always remember, output of the integrator is the state, not the input. Okay, output of an integrator is the state. Subsequently, this becomes the input to the other integrator. However, always see that the output of the integrator is defined as the state. So the states are defined in the reverse order, as you can see. So x1 is the first state, which is the last, which is the output of the last integrator. Xn is the last state, which is the output of the first integrator. So that is also mentioned here, and I think this is all. And if there is something else that is also written here, you can go through it. So these are the observations that I made, I had personally made from the from looking at the transfer function and the block diagram. You may find some other patterns which might be useful for you to remember. So sometimes what happens, sometimes we also give a question where we directly ask you to draw the block diagram. Okay, so you need not pass through all the derivations of the state space representation. Simply looking at the transfer function, you will be able to draw the block diagram if you remember this correspondence between the two. And please correct this should be negative. Now we come to another representation of the same transfer function. This is also the first companion representation. However, this is a bit different, and here the block diagram we have changed. So since this is still phase variable, what will not change? The dynamics, the style of the first order ODs will remain the same. However, you can see that there is some change here. I will discuss that, what is happening. However, what has not changed in the block diagram, try to understand that. What has not changed in the block diagram is the way we have defined the states, and we have passed them we have made this chain of integrators. And this bottom part looks very similar as before. However, something has happened here. What has happened? We had tried to include the input into the this control input u into the input of all the integrators. We have tried to incorporate this control input in the input of all the integrators. That we have done. So what happens here? Instead of simply x1 dot being x2, x1 dot now is x2 plus p1u. So x1 dot is still x2, but there is also some control input getting directly added to it, added to the dynamics. x1 dot becomes x2 plus p1u. So if you consider the unforced system, then the previous first companion form and this alternate first companion form will remain the similar. The state dynamics will remain similar if we consider the unforced system. So the basically what will not change? Unforced system means u becoming 0. So what will not change is A matrix. The A matrix will remain same. So the A matrix is basically the identity of the form. So whenever we will talk about different representations, different forms, the A matrix will identify these forms. So first companion form or the phase variable form has a definite pattern of has a definite signature of the A matrix. The A matrix will be like that, and we have already seen that the upper diagonal is 1 and the bottom row is having coefficients. So that is the signature of phase variable form, be it alternate, be it original, be it whatever. Phase variable form means A matrix is like that. First companion form means A matrix is like that. Other matrices B, C, these will change for these alternate variations of the same form. So here you see by looking at this different block diagram, differently represented block diagram, these are the equations that comes to us. These are the equations. We can easily formulate these equations. x1 dot is x2 plus p1u. Similarly, all this will happen, and xn minus 1 dot will be xn plus pn minus 1u. xn dot will be all these terms getting added, so minus n x1 minus n minus 1 x2. So I have put the minus sign in this one. I have corrected. I had forgotten correcting it in the previous ones. So please note this, and in your notes you must give the correct block diagram. So all these things and this p and u getting added, so that forms xn dot. What is y? Y is x1, but this p0u is also coming, x1 plus p0u. So what is the difference in the alternate? We have tried to forcefully include u in every dynamics and in every equation, in the state dynamics as well as in the output. We have forcefully tried to include u in the block diagram itself. In the block diagram itself, we have forcefully tried to include u. So this makes the dynamics like this. Now on doing this, what actually we did, we introduced these coefficients p0 to pn, which were not given to us from the transfer function. Realize this. I hope you have already noted this by this time. This p0 to pn, these coefficients were not given to us from the transfer function. We are converting the transfer function to the state space representation, not the block diagram as such. Okay. So we are going through the path of the block diagram in this case, but we could do that only when we already knew the block diagram of the original first companion form. So now we are playing with the block diagram. However, from the transfer function, we don't have the knowledge of p0 to pn. So p0 to pn we need to evaluate. So that is the task now. Let us see how we are doing this. So these are the equations from the block diagram. Already we have seen this. What we do, we take the output and differentiate it successively. So here the differentiation of the output is happening. Y is this, then we see, then we find out what dy is. What is dy? dx1 plus p0 du. Now dx1 basically x1 dot is already known from this equation, so we always refer to these equations which we have derived from the block diagram. x1 dot we write it down as x2 plus p1, so dy becomes x2 plus p1 u plus p0 du. Then we do this d2y, so again another d operating on this equation. Then x2 dot will come and p1 du will come, p0 d2 u will come. x2 dot again is x3 plus p2u. So we write x2 dot as x3 plus p2u. Similarly proceeding, we can observe that finally dn minus 1 y will become xn plus pn minus 1 u plus pn minus 2 du plus dot 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 p1 dn minus 2u p0 dn minus 1u. So you can do this in pen and paper, and then you will realize. So once you do one or two, you will find the relationship and understand the general behavior, and you can very easily find out what dn minus 1 y is, and you will find out this expression. Then what is dny? Another operation by the differentiation operator. We will get xn dot and all this du, d square u, all this will come. So this du, these are very easily verified, and this xn dot we have taken from here. Xn dot we have taken from here, and in the xn dot expression we also have a pnu. So that pnu is missing in this expression, you see. So I have missed the pnu here, so you should also include that pnu here. So there would be a plus pnu, the first term should come as plus pnu, then pn minus 1 du, pn minus 2 d square u, like this. So include the pnu here when you are doing your notes. So this is the expression of dny. So what we have now, we have the expression for all the different orders of derivatives of y. We have y, we have dy, we have till dny. So where we will use this? We already have the transfer function. We know the system dynamics from the generalized transfer function. We can do that, right? We can take the denominator this side and the numerator that side. Understanding that how that sn ys is basically dny, and likewise, so we can write the transfer function in terms of the a series of in terms of this in terms of the differential equation, which is the system dynamics, So this differential equation can be written from the transfer function. Now here all this left hand side derivatives of y had already been computed. The expressions of this has already been computed. So we put this. So we first evaluate this left hand side by substituting all these d's, all these dy, d square y, all these different orders of derivatives of y. We put it here and we get an expression. And this expression is in terms of u only. You will find this. So you have to calculate this. You have to do some more steps. This is the final step what I have written here. There will be some more steps involved. So you do that by your own hand, because as you see here in this all these expressions, the different state variables are already also present. However, in the final expression no state variables are present. So the state variables will get cancelled out. So how they are cancelling out, you will only understand if you write the intermediate equation. So you write that intermediate equation, and it is very easy to see how these state variables will get cancelled. You will only get this final expression where you have a coefficient of u, you have a coefficient of du, you have a coefficient of dn minus 1u and dnu. So you will have these as the coefficient. So and this coefficient expression of these coefficients are what you need to look at. You notice that the coefficient of u is longest and the coefficient of dnu is the shortest, only p0. That thing you notice. Now what we do, we will simply compare the coefficients with the right hand side of this system dynamics. The LHS of the system dynamics we have computed, so this must be equal to the right hand side of the system dynamics, and by looking at this expression and this expression, we see that we have all the terms same. U term we have in the LHS as well as RHS, du term we have in the LHS as well as RHS, proceeding till dnu term. Till dnu term we have in the LHS as well as in the RHS. So we can compare coefficients. So we do the compare coefficients exercise and we come to this set of equations. This set of equations are obtained by comparing the coefficients of the different order of derivatives of u. Different order of derivatives of u. So comparing the coefficients of the different order of derivatives of u, we find this set of equations. So very easy to note one or two. As you see here, dnu is p0 in this side it is b0. So p0 is directly equal to b0. dn minus 1u having the coefficient of p1 plus a1 p0, which is equals to b1. It is simply b1 in this case. So this long expression, which is the coefficient of u, this long expression, that will be equals to bn. Similarly all the other expressions can be seen here. By studying this set of equations, you will be able to discover, this will take a bit of your expertise in your handling of matrices and vectors. So you might not be very easily able to identify this. However, you can back calculate. When you back calculate, you will land up on the same equation. So what I am doing is basically I am writing this set of equations in terms of matrix equation in the next slide. So this is the equations already there, which you can refer, and this can be written down in the matrix format like this. In the matrix format, if you write down, the RHS is this you can easily identify. RHS is b0, b1 and all this up to bn, and we have broken down the LHS into these two, one matrix and another vector. Why we have done so? Because this is the vector we need to evaluate. These pi's are not given to us, ai's and bi's are given to us, but we have written down the system. We have written down the state space realization in terms of pi's, not bi's. In terms of ai and pi, we have written down the state space realization. So we have to find out what these pi's are in terms of ai and bi. So we have expressed this in this form, which is basically a form like ax equals to y. So a being a matrix, x being a vector, y being a vector, a and y being known, we have to evaluate x. So in that form it has been put down. So now for solution, for having a unique solution of that x, you know that that A matrix must be invertible. So you must have this A matrix invertible. That means the determinant of that matrix must be non-zero. So we must check the determinant of this matrix if it is non-zero or not. So by the way, this matrix is called the Toeplitz matrix. Toeplitz matrix is where you have the upper diagonal or the lower diagonal 0, and the diagonal element and the subsequent ordered diagonals, like this is a lower diagonal and then the next lower diagonal, then the other next lower diagonal. So all those diagonal elements will be same. That is the Toeplitz matrix. So all these diagonal elements are same. The main diagonal elements are 1 here in this case, the next one is a1 in this case, the next one is a2 in this case. So they are equal. So that is the identifying feature of Toeplitz matrix. So here we get a Toeplitz matrix. So the Toeplitz matrix, the determinant of the Toeplitz matrix is basically the diagonal elements raised to the power of n being the order of this matrix, and here the order is n plus 1 basically. As you can see, it's starting from 1 and ending at n. That means 1, a1, a2 and an. So a1 to an there are n numbers, and there is another here 1. So there is basically n plus 1 cross n plus 1 matrix. However, the diagonal elements all being 1, the determinant of the matrix is basically 1. So we don't need to bother about what exactly is the determinant, but it is non-zero. That is what we are bothered about. So it is always by this observation we can conclude that this set of this uh, p coefficients which we incorporated in the block diagram forcefully, now we see that we can calculate them uniquely. So then whatever procedure we have followed is justified. So we are not landing upon in a situation where we have followed a procedure and assuming some unknown, and now we are not in a position to evaluate those unknowns. We are not in that sort of position. We are in fact able to evaluate these unknowns uniquely. So whatever approach we have undertaken, that is a valid approach, and it will give us a state space realization. What is that state space realization? Ax plus bu cx plus du already we have seen, and if you go back to the equations, the equations had already been written down. Actually our problem was only finding out these p's. The state space realization was already made from the block diagram very directly. Our problem was to find out this p's, for which we did a few calculations. So looking at this state space realization, we can immediately see that a remains same. So the form is basically still first companion at the phase variable. What had changed? B has changed, because we have incorporated u in each of the dynamics of x1 of xi. So each of the state dynamics is having u coming in, and it is coming in through all these pi's, and now we know what these pi's are. We can use this equation to evaluate these pi's. However, we have written them in terms of this pi's only for the sake of convenience. And here what happens, c here is simply x1 plus p0u. If you don't remember, y is simply, from the block diagram, y is simply x1 plus p0u. So all this exercise actually had been done in order to simplify the c. So in the first companion form, b was 0 0 0 0 1 and c was having all those coefficients. In the alternate first companion, c is 1 0 0 0 and b is having all the coefficients. So we shift the burden of the coefficients, if I may say, though it is not a burden as such. So we shift the burden of the coefficients to b matrix instead of C matrix. So in this case we are dealing with CISO systems basically, since transfer function is basically for CISO system. So it is a vector, this is also a vector, and d will be p0, x1 plus y is x1 plus p0 u. So d is p0. So that is the thing. So if we have p0 equals to 0, then many things will become simplified. Basically the calculations will become simplified. P0 is 0 when P0 is basically B0. if you remember. So you see here also p0 is b0, so p0 will be 0 only when b0 is 0. So note that a remains same. So that is the thing to note. So here is the end of my lecture for the first component form and its alternate representation. In the next lecture we will go for the second component form, which is also called the rectangular form, and we will derive it, and we will also observe the differences with the phase variable form. Thank you for paying attention. Goodbye.